Okay. Compact. All right, let's get started again. We'll get you out of here for the end of the day on a Friday. So I appreciate that you've all stuck around. So we're going to talk a little bit about the quantum education and workforce development work we've been doing here at Mason. You've heard a little bit about sort of the context for all of this from Dr. Akers and Dr. Peters and then Dr. Singh, who are all tremendous experts in this field and have really laid the groundwork for a lot of the things that we're doing here. And I will say, like the Q12 work that has been done to lay out some of the key concepts and various other things that have already been talked about are the origin where we've started for a lot of the work that we've been doing. So in the work that we've been doing, and unfortunately I can that's a little bit. I don't know why it's showing all the bars, but we're going to leave it like that to at least give you a sense of the various people who have been working on some of this effort here at Mason. And it's really a broad effort that's focused both on the education in quantum as an interdisciplinary field for our undergraduate and graduate students, but also thinking about what we can do at K-12, because as Dr. Singh pointed out, it's really key to start getting kids engaged with these ideas early and make sure that we're engaging them and interesting them so that hopefully by the time they get to us here, we have a more diverse population than what we have been seeing coming up through physics and math and computer science and all of sort of the natural feeders into this field. As an astronomer by training, I also tend to view it a lot as, you know, what are the cool things that we can show kids? How can we get them excited? Quantum has some really interesting things to think about and get them excited. And how do we use that at the K-12 level? But then for undergraduate education, what opportunities are available? What courses should we be offering? How do we make them how do we create things that are interdisciplinary within the university system? Not always an easy thing to do. And what programs should we be developing, especially as we think about experiential learning, other opportunities to really do hands-on work at that level, and then on to graduate education and what do we need to develop to really prepare that level of workforce for the field, because it's going to go across all of those levels as we develop it. And so we've got a big team who's interested in different aspects of that we've been working on. And so why quantum? I think I'm not going to obviously spend any real time on this, but of course it's in the news, very buzzy. Right, everybody's excited about it, but I think they're excited about the potential for these systems to become robust enough that we can really start to do some exciting work with coming quantum computers, with quantum sensors, with quantum communications, right? These are all things that we need to start thinking about and developing that workforce for. And industry is telling us they really do want to start hiring in these areas. And so our approach really is, in terms of the who should learn about quantum, is that everybody should know something about it, right? Maybe to very different levels of depth, depending on interest and where they want to go. But to make an intelligent and informed decision about whether this is a path you want to take and something you want to dive into, you need to know what it is. And you need to have that opportunity, hopefully, to get excited about it and see whether this is the thing for you so that we can pull people in and get them interested at an early age. I do want to point out that our group is in all of this invested in the research portion of it as well as in developing programs, because as we do this, we really need to understand questions about how people learn to understand quantum concepts. Who is doing it? How do we broaden participation? How do we make this an equitable field, right? How can teachers bring it into their classrooms and where? And that'll depend on what they're teaching and at what level, right? So I think Dr. Singh really gave you some of a flavor of the kinds of things that can be done. He's been a tremendous leader in doing a lot of this education research. And so we're starting to look at how we can do that as well. from basically K to 20, as we say, right? From elementary through graduate school, and as we develop programs, really examining the work that they're doing, their efficacy, and how they work. And so also to point out, right, the physics education research it's a scholarly area, right? We're developing research groups. We have graduate students doing research. We have had students here to pursue PhDs. Hopefully, unfortunately, a couple of them decided they wanted to go teach. So we're looking for new ones, but this is an area you can actually do as a research thread. So I did want to make sure we point that out, in addition to getting involved in just sort of the programmatic work that we do. So what are we doing for K-12? What have we been developing? We got a grant from the Department of Education that was actually a congressional earmark that our representative was able to kind of get through Congress for us. And so we have been looking at how do we develop programs in this area. And there are sort of three pieces to the programs that we've been developing. One is what they refer to, and I've learned this from doing it, I've not done a lot of K-12 before, these experiential learning opportunities, which are, the problem is if you say internship, that's very strongly defined in terms of number of hours. So this is anything that gets students out of the classroom, doing stuff, getting involved, seeing kind of what the workplace looks like in research labs in industry. So we piloted a program last summer for high school students to come in, well, virtually first learn a little bit about quantum and some of the basic concepts, and then spend a week visiting places that are doing quantum related work in the DC area. And we're going to be running that again this summer. So we're excited to start recruiting students for that now. Our applications are open. So, you know, rising seniors who might be interested, or who know rising seniors who might be interested, we can provide that information. In addition, we've been doing a lot of work with teachers and teachers across K-12 about what is quantum and how can they maybe think about bringing it into the classroom. Again, because our idea has been that we want to make sure that it's in a broad set of classes, that teachers becoming familiar with it so they can bring it to their students and introduce them to it. I think Dr. Singh mentioned the polarization activity. We've been doing that with teachers so that they can bring that to the classroom. And we're hoping to really be working towards curriculum development, which is much harder, right? How do we actually build things that can be used in the classroom and that they can take in there and actually present? We've been working with the small amount of material that exists right now at that level and thinking about what are the next steps. This summer, we're planning to have a more extended opportunity for teachers to come in and really think about what they need to design for their classrooms as part of this. So just a little bit more about these programs. I mentioned this high school program, some of the pictures from it. One of the exciting things about it actually was not only did they do this virtual course, followed by their sort of week in person doing stuff, but afterwards, the Quantum World Congress was in DC this year, and we presented them the opportunity to put together a poster. And this wasn't your like, oh, you've worked in a lab this summer, describe what you've done. It's you've heard a little bit about quantum. There are things in the world, problems in the world that we're interested in as rising seniors. So what we want you to do is go do a little bit of research, just learn about one of those problems and how quantum might be able to actually have an impact on it, whether it's related to neuroscience. I think somebody did waste disposal, someone did quantum dots. So it was sort of someone did communications, with space-based communications. So it was really sort of all over what they were interested in to research, and they came and presented at the Quantum World Congress, which was really great. It was really a highlight, both for them and I think for a lot of people at the conference. It got a lot of attention from people who were there. And I will say one of the most exciting things about it to me was that there were several students in the program who signed up because they were interested in STEM generally. And I think partially didn't already have something committed for the summer. That sounds kind of interesting, but they were much more interested in medicine and biology and didn't think this was necessarily the thing for them, but were kind of curious and came and having visited some of the labs that do some of the sensing, like biological sensing and various other applications, we're really intrigued with the possibility that this was a path that they could possibly get involved in and see themselves doing, even though they're like, we don't want to do programming, right? And I think they had thought of this as maybe more programming oriented when they came in, but found sort of a piece of it that really engaged them and excited them. I think maybe speaks to some of the ways that we approach it in the future. So we learned a lot, right? As I said, I mean, some of this is what I just said. But one of the questions is, how do we reach kids that aren't sure they're interested? We got a little bit lucky with a few of them. One of the other things that we found was that we lost a couple because of transportation and financial issues. So part of the point of getting this grant was so that we could pay them. But even with that, transportation, we realized was a really big problem. We're actually going to house students on campus this summer, at least from what we've been told, that hopefully will alleviate some of those problems, but we'll see how that works. So some of these barriers are a little bit harder to see, right? And so we're really trying to dig into what are they and how do we alleviate them and where do we run into them to make sure that this is accessible, but it's not easy to do. On the teacher professional development front, we've been, as I said, working with teachers to do all of this stuff and introducing them to it. We've had them across from elementary through high school. And I love this quote. One of the things that we tend to ask the teachers at the end of the workshop, and it's a most of the day workshop, right? It's 5 hours. It's not a ton of time. They're really just getting the first little bit of flavor of what is all of this about, and leave with some resources that maybe they can use and bring to their classroom. Although I take back, I think this quote at the bottom may be a group that we had over several virtual meetings last summer. We've had several different formats. But we asked them, what did you used to think about quantum? What do you think now? Or what are you going to do with that knowledge? And we actually had several where they used to think was of this order, right? Quantum science was just something from the Big Bang Theory. There's quite a few people who end up saying something to that effect. Big Bang Theory comes into that a lot. Clearly, that's sort of in our conscience of, sort of popular ideas about the world. But to then say it's, now I think that it's accessible and necessary for students to learn these concepts. We're headed into the future with the science. And so saying that they'll continue to learn more, help teachers grasp these concepts in order to pass the information and excitement along with students. So the challenge is that they're liking it, they're seeing the point of it, they're engaged, now getting them comfortable enough with the material that they really feel like they can bring it to their students. But we already have one elementary teacher who has created like a club for students in about quantum, to find out more about what she's doing. And so it's starting. We're starting to actually see things happening, which is very exciting. They're very, so as I said, they're very receptive to bringing it into the classroom, especially the elementary school teachers. I will say more than sort of from the ones that we've had, they have probably been the most receptive, I think partially because they've got the greatest flexibility in bringing new things into the classroom. And there are a very small number, but really good resources that talk about things like measurement for young kids and what does quantum measurement look like versus classical measurement. Why are they different? And superposition. And one of the teachers that we work with always likes mentioning the sport, and that is a superposition. But even some of the other activities, when they talk about superposition, and there's a book, and a couple of the teachers came back and said, we could do this with the social and emotional learning exercises that we have to do all the time now, right? Talking about being in these two emotional states at once, especially for the little kids, and what that looks like and what that means. So they're excited to think about it and work with it. The physics teachers have a little bit better grasp of it, but I think for them it's harder to figure out where it fits in the curriculum, with the exception of like some of the IB classes and others where they, or maybe at the very end of the year, right? So it's like, oh, well, we can squeeze this in. So we've started also with mostly curating existing materials, right? We didn't want to start by creating our own. And that has been quite effective, right? Is pulling together what's out there, letting teachers take a look at it and think about how they might actually. All right, I'm gonna turn it over to Ben and let him talk about what's going on there.
Okay, so all of that was K-12, and now we're going to talk about quantum in higher ed. So we're looking at our students here at Mason, but also beyond. So we already have all of our physics majors take quantum mechanics, but as you've been hearing about all day, like quantum goes beyond just physics, it's an interdisciplinary field. So we're looking beyond just like what students are doing in physics and looking into this as something that can be for students across multiple disciplines here. And so to do this, we need to understand what the needs of our students are, and as well as the needs of the coming quantum industry. So part of what we're doing is researching this and figuring out how to do this, and we need to prepare students in a variety of ways for a variety of outcomes. So quantum is something that's been historically taught in upper level undergraduate or graduate physics. So this is something that students don't even get to that until after they've taken at least 3 semesters of physics and all of the math prerequisites that go along with that. But we want to find ways for students to encounter and to understand these ideas of quantum, even if they're not coming in with all of this physics and math, and have other opportunities for students to learn quantum without that. So this is a study from 2020 that was from Fox, Wickel, and Lewandowski in Physical Review of Physics Education Research, looking at the jobs that are out there. So they did a survey of different companies that are doing quantum, and looking at the job that are out there. So this is the colors. It's hard to see here, but these are the different jobs that are like technician, engineer, experimental science theorist, application researcher, and what degree subject and degree level people are at. So we have people who are like degrees like in physics, engineering, computer science. So these are PhDs, but then there are also plenty of jobs that are there for this master's, this bachelor's. So there are plenty of quantum jobs out there for people with bachelor's degrees, and this is like the percentage of which company is reporting. So like 57% here like had people with bachelor's in engineering, this is bachelor's in physics, master's in physics. So these jobs are out there, and to look at our students' understanding and interest in quantum, we did a survey looking at lots of undergraduate students here. And so one question was asking them what they know about quantum careers in general, and the majority of them reported that they know nothing, and then you have these who reported that they know a little bit about quantum careers, but so most of them were not reporting that they know very much about it. However, so the question about whether they are interested in pursuing a career related to quantum, these are all the people who said that they agree with that statement. So even though they report that they don't know much about quantum careers, it is something that they are interested in. There was an open-ended question on the survey, just asking them to explain like what they know about quantum careers. So a good number of them just said that they know nothing, but some of them, when they were talking about quantum careers, they were connecting this to quantum computing, and others were connecting this to theory and to research, like in physics and in engineering. So this is some of what students have said about this. Like one student said, the first thing that I think of is to be really smart. Others have said you probably need a PhD to realistically get a career in the field, and even then the positions will be competitive. Another student said what they know, not much, just that it is hard. Someone else said there's not a wide range of jobs in the field you're taking a risk studying in. So this is where students are at right now in terms of their understanding of these careers. A lot of them are seeing this that is not something that is accessible to them right now, but a lot of these students were fascinated by it and wanted to learn more. And so for what they're looking for, one thing is college classes that are accessible. So one student said some of the class restrictions are a little frustrating. Some quantum classes are only for graduate students or people within that major. So one goal is to have classes that are more accessible to this wider population of students available to undergraduates who are not necessarily majoring in these things. Other students have talked about wanting to have workshops and lectures with videos that they can watch at a different time. So one student said, I'm definitely a part of the YouTube generation. So how I got into most of my interests, but I'd see a really cool video of someone doing something. So this is like also they reported where they learned about quantum. So the largest number of these said that they know about it from the media, whether it's internet news, YouTube videos, documentaries, books. Some students reported that they learned about this from high school classes, and we have a fairly wide range of different types of high school classes where they reported hearing about this, whether this was physics, chemistry, computer science, technical drawing, and then some of them from professional experiences, and then a fairly small number learned about quantum in college physics classes. Like if they had taken physics classes, a lot of them, like maybe it was just the intro level physics where they don't get to quantum yet. And so and then we kind of have students again saying like for me it was YouTube. So these videos on YouTube had mathematical explanations of quantum physics. Those two are my most meaningful sources. So these are different places students are learning about this. So some of the ideas driving program development, like what we can see from all this, is that building a diverse workforce in quantum mechanics is going to take work. Students don't know much about quantum or quantum careers, but they are interested in learning more. So they're interested, but they think it's hard, and this is a barrier. And so students do want to learn more about quantum in accessible courses. So examples of this might include freshman seminars or lower level courses, like things that students can get into even if they haven't been through all of these other physics and math courses before that. And small amounts of content can grab their interest. Like you see these students reporting, they watched this video on YouTube and then they got really interested in it. So one student said, inspiration goes a long way. I remember I watched a video where a professor talked about when she was first in the lab, she was super inexperienced, but now she's an experimental physicist. I think things like that where people share their stories can help.
Yeah, so that's what we're hearing from students, right? There are barriers that we're seeing definitely into how to get them engaged, but there are also opportunities. So we've been working to try to sort of build out what exists for students. Dr. Tan teaches a course on quantum communication, quantum computation, quantum information. Garrett teaches a quantum algorithms course. There are now seminars in computing and sensing, research opportunities and industry opportunities. We've developed an MS track, a master's track within physics and quantum science and engineering, but really tried to design it so that the prerequisites are pretty limited, so that you don't need to have taken upper level physics courses to pursue it. So if you're coming from another major and might be interested in doing that, it should be open and available. We're also currently planning on trying to develop a master's that is much more interdisciplinary and crosses some of those departmental boundaries. So one of the things that I'll pose as we get to this is, getting some thoughts from all of you. What is it you want to see? What would be most useful as we look to develop things at Mason? This is just the information about the quantum information science and engineering concentration in our master's program. So there's a GoGMU link that you can get to and find out more. And so there's lots going on, and we'd really love to hear from you. What is it you want to get involved with? What is it you would like to see available as we go on? And I will stop. Yeah.
I didn't realize you guys were so much into K-12 education. What are you doing to find kids to come participate?
Yeah, so that's an excellent question. So the one program we've been running with the kids, right? We've been doing a lot more with the teachers, and I will say we're all sort of I feel like I'm just getting into this area. One of my colleagues, Dr. Holinchek, is really our K-12 expert. And Dr. Gracious was in K-12 for a while too. So between the two of them, I rely on their expertise. So we piloted some of these things this summer is this program for high school students, which we're advertising now, which we have tried to do through our teacher networks. We work with a lot of the administrators, although it's not always the best way to get to the students. And we're trying as much as we can to go to school. So one of the things that I'm doing next week is going actually with DC has a program where they provide work experiences for DC residents, for kids who are DC residents. And so there's a thing that they can go to find out about jobs that are available. So I'm going to go and talk to them, and we have this money this summer, so we can also pay it. So I'm hoping that will help to recruit, see who's interested, who we can get. So we're doing it that way. We worked at least last summer, and hopefully we'll be able to this summer, although there's some challenges with Montgomery County that has also a program for kids to try to get them employed and getting sort of internship experiences. So we're trying to get our fingers into those networks, which are working to both combine those from previously underrepresented groups in these areas with sort of getting them to hear about the program and apply and get into it. So, but it's tricky, and that's part of why I asked the question of Dr. Sayhouse, what she's thinking of, because we're always looking for ideas, and I found it to be hard.
It's so difficult to get the word out.
Yeah, getting the word out is tough.
And then when you find that, you have programs here at campus, or are you going to their school for both?
So mostly we've been doing it here at this point. Partially that's people power. And so, you know, and as I said, we've sort of been piloting these things. I think there is definitely an interest from teachers to go to schools. So we're thinking about how we can maybe do that. But well, let me back up and actually say mostly that's true. But one of the graduates who was here earlier works, MAP has a program at Mason, has a program called MEGL. And they do a lot of workshops in schools, mostly elementary, some up to middle school. And so we're working with them, and probably going to do a couple on quantum algorithms in a couple of the local elementary schools in the next few weeks. So trying to do that in the ways that we can and with the groups that we can, but there's a lot more to be done. Thinking about how to scale is really the challenge. But it also is about developing materials that are going to be good for that. And I will say, I mean, this is another opportunity. We have the picture that's up there with us, which is a good advertisement for our game session next. But we actually developed this game session and ran it the one other time we did when we were asked by the university. They had invited the middle school finalists for the science fair, the Broadcom Science Fair, to campus to do a couple of workshops. So these are middle schoolers. And would we do something on quantum? And so what we did is what we're going to be doing here at 4:30, which is create a quantum game out of a board game that exists. So that's Chutes and Ladders. So we will show you our version of quantum Chutes and Ladders, which we're still working on, what the best way to do those rules are. And then tell them, here are a bunch of other board games. Figure out how to develop quantum rules for them. So this was one group that, despite the fact that telling them that Monopoly probably was going to be really hard to do this for, of course, picked Monopoly. But anyway, that's the kid for you. So that's kind of what we're trying. Yeah.
I have two questions. First, earlier on, you guys were showing survey results of undergrad students and like what they said, what their exposure to quantum education was, quantum careers, I think. So like in that group of students, you said undergrads, are they what I'm interested in knowing what majors they are.
They were STEM majors broadly. I didn't put in here, I should have. We've been looking at also how it broke down by majors, because a lot of STEM majors, or at least the science majors, or biology. We had a bunch of engineering, we had sort of engineering and biology, and then of course, pretty well matched our STEM majors, sort of statistically across the colleges.
The reason I ask is because, like one part of the presentation was about K through 12 quantum education, which is like, the broadest that you can get, because literally everyone does K through 12, right? But then in the higher ed setting, it's more like, STEM, like you said, right? So it really does somewhat, it's interesting to me how you guys would introduce, the idea of teaching quantum to one set of students that's more STEM based and actually has experience with the technology to a certain extent and science, versus teaching a different group, K through 12 students who are extremely basic, like don't even understand calculus, right?
Right, and I will say, what's interesting is, while probably I would have come in with that idea, right, that they're pretty far apart, the reality is that for most of our students, until you're at a fairly high level within a STEM program, or juniors and seniors in physics or whatever, quantum's still pretty foreign. I mean, admittedly, right, you aren't all physics people or people who've necessarily crossed it in their majors, because we took STEM quite broadly in the survey, but most of them had no idea what it was, right? And even when we interviewed those who were most interested, well, there were a small number who could speak very well to what is quantum, why is it interesting. Even most of them struggle to really explain, what is quantum? Why is, what is this all about? So I think the reality is that those two things are not as far apart as one might expect, which really also speaks to what we need to develop to help get students engaged in quantum. And the fact that when they're getting to the university campus, they're still at a fairly early stage of it. Yeah.
And,
If somebody like that's the vast majority of our STEM majors, they are not currently doing any quantum, like if they're physics majors, they are, and maybe chemistry, but but right now, like if somebody, for example, is computer science, like most of them are not doing anything with quantum, but that is like having that computer science background is something that they could then build on towards learning about that. Like if there were going to be something with quantum computing that they could do so they in some of these STEM fields, they may have relevant background that would then help them with quantum, but currently most of them are not doing anything with quantum as it is.
We have one more, and then we'll get to, yeah. No.
So, well, my second question is not really a question, it's more actually an answer to the question that you posed to us earlier about what else could be done about, furthering on your work. So I'm a grad student. I come from a computer engineering background, and my specific focus is on architecture design at the hardware level, especially. And well, that's one of the things that really interests me about quantum, and particularly quantum computing, is how does quantum hardware work, right? So I'm wondering what kind of I guess classes or workshops, what kind of stuff would you guys have to try and introduce how quantum hardware specifically would work?
So
like
I'll take
hardware.
I don't know, I was gonna say, I'll leave the experts to that one.
So this is did you want to answer?
Yeah, no, so basically, this is, I actually represent computer engineering, so that's my major. And we are very open within our faculty to start concentration in quantum computing within the program in computer engineering at both bachelor's level and the master's level. Obviously, we have relatively a small number of faculty members that have expertise in that area, so we are very open, for collaboration with all our departments, and we will not be able to do it momentarily. But we already approved one course that is being taught by Professor William John, quantum computing design systems. The plan is to extend it and possibly combine it with courses offered by the physics department and create this opportunity. At the undergraduate level, we need just 3 electives to form a concentration. At the graduate level, we need kind of 2 required courses and a few electives. And if we work together, I think, that's possible within a year or two. And the possibility to get it to the cutoff. Why computer engineering is a good story. I think it kind of looks at the whole stack, starting from algorithms at the top and going to qubits at the bottom. Students are interested in learning about compilers, technology, instruction set architecture, how gates look like, the electronic that communicates between, allows instruction to be executed on qubits and so on. There is this basic understanding, how it works in classical computing. So you can, by analogy, try to understand what is different, what is similar between these two technologies. So I think we have definitely interest for a lot of good books already written on the subjects. We not specific necessarily to the physics department, physics major, but are more open to engineers. And I would just encourage everybody to get involved. We have thinking about concentration with different and sharing courses. So, for example, the course on quantum algorithms, that would be a fantastic addition to our concentration. As long as it does not have prerequisites which are very specific to non-engineering students. If our students take this course, that would be fantastic.
So this is kind of a philosophy we want to start having for courses related to quantums to make them bridge disciplines. We want to avoid prerequisite and we want to make it so that what we're teaching is accessible. And I don't think you were necessarily here yesterday, but some of the main we did a survey of 57 quantum companies. And mostly what they want is not you to do a full physics major. They mostly want you to have a few courses that would give you a concentration in your discipline of choice. So to be an excellent ECE student with enough quantum to be literate, if you will, in it. Some ideas we have about going beyond coursework alone are being explored as well. There are new facilities opening up where we're hoping to maybe have some hands-on experiential learning where you could be making quantum entanglement measurements with photons, learning how to use cryogenic systems. The new clean room on the SciTech campus will allow us to have our students here at the university get some experience in lithography, device processing, device characterization. I was made aware of a really neat, I wanted to talk to you about this actually, because this might be really useful for a part of your course, but IBM just deployed a qubit simulator where you can called QuizKit Metal, where you can design your own qubit and then simulate its performance. And so it starts to go from what, as a computer engineer, you do get this unique perspective where you see the entirety of the system. And that's not something that you get in any other discipline. So up until now, everything in quantum, in my opinion, has been focused on the software and writing software and executing it on a computer. And there hasn't been much in hardware, but that's starting to change now. So, that's something we're hoping to implement together in the future, and to do so while thinking about how we can bridge across our different disciplines to make sure, wherever you are, you can enter into these really cool job opportunities, really cool area of science and technology.
Thank you. All right, so we did it. Thank you, Jessica. Thank you, Ben.